Before we get into problem number 1, you should have already worked on the front page of your review packet, which has all of the formulas that you need, and you should have those handy because we are going to be using them, and you want to be able to know where they're at for different types of problems. So if you've not already done that, I would highly recommend going back and filling in all of the formulas from your notes onto your formula sheet. Okay, so problem number 1 says the area of a circle is 35 pi square centimeters. Find the circumference of the circle. So in a problem like this, I'm seeing that they are telling me about the area of a circle. So the very first thing that I'm going to do is I'm going to say that the area of circles looks like pi r squared, right? So we're going to just write down the formula. And then we're going to write down, they just told us that the area is 36 pi. So I'm going to say this is 36 pi. Okay, A is 36 pi. Okay. And now I'm going to figure out kind of what do I have and what do I need to find. And if you take a look, it's really basically the pi on both sides is irrelevant. So it looks like the r squared represents the 36. And I could do that algebraically by just dividing by pi on both sides. If I were to divide pi away, okay, these cancel. And it literally is going to say now that r squared is equal to 36. So when I square root both sides, what I just found out is that the radius of this circle, okay, is 6. Okay, so I used what they gave me. When I saw the area of a circle, I just started with the formula and I worked my way from there. So now they're asking me to find the circumference. So we're going to say now the circumference is equal to pi d. And remember, a diameter is the same as 2 radius lines. Okay, so we're going to say c is equal to pi times 12. Okay, and I'm just going to write that in the standard form, which is 12 pi. Oh, I wrote 11 pi. Let's try that again. Okay, so we're going to say 12 pi. Okay, so it just looks like this. Okay, and when we're doing a circumference calculation, our units are not square units. They are just regular old units. So we're just going to say in this case centimeters. So my answer to the first one, 12 pi centimeters. Okay, so problem number 2. It says a rhombus has diagonals of x minus 6 and x units in length. If the area is 8 square units, what is x? And in big bold letters, they're saying be sure to eliminate answers that don't make any sense, right? So if we're saying that, for example, a length is negative inches long, that wouldn't make sense, and we'd have to throw that one out. So let's see what happens for our problem. So a rhombus, okay, again, they're talking right here. I'm going to look for my key phrases in the problem. This says the area of a rhombus, right? And so what I'm going to do is write down the area of a rhombus formula. So we'll start off by saying that the area of a rhombus is equal to 1/2 diagonal 1 times diagonal 2. So D1 and D2 stand for the length of the diagonals, and that's what they told us here. It says a rhombus has diagonals of x minus 6 and x. So now I know to plug in D1 and D2 is x minus 6 and x. So I'm just going to rewrite this now and say area is equal to 1/2 x minus 6 times x, right? That's kind of the plug-in step, okay? And then I'm going to keep reading. It says, if the area of a rhombus is 8 square units, what is x? So actually, the other piece that they told me was that area, A, is 8 in this case. So I'm actually going to erase my A here, and in its place, I'm going to put an 8, okay? So really, I just have to solve this equation now. So let's see what we can do to clean this up a little bit. So the first thing that I'm noticing is that x and x minus 6 can be multiplied together. X times x minus 6 is just a distribute. So I'm going to say x squared minus 6x. All right, and then I have this half sitting out front. I got to figure out how do I want to deal with this half. So again, let me fix my poor writing. Okay, so this is going to say just a 1/2. Okay, so we could, and we wouldn't be wrong, if we distributed this x into the parentheses. But I don't want to do that because, remember, my goal is to get x to be by itself, which means much more simple than it is, okay? And if I start giving a half to it, it's going to actually make it more complicated. So another thing you can deal with, instead of multiplying a half in here, is if I multiply the right-hand side by 2, 2 times a half is a cancel. It'd make it just go away. I'm trying to get numbers away from the x, so it makes sense to do that. And the other thing that I need to change then is that I need to multiply the left-hand side by 2 as well. Because I multiplied the right-hand side by 2 to get rid of the half, the left-hand side needs to do the same thing. So now it looks like 16 is equal to x squared minus 6x, okay? Any problems that have squareds in them, or I won't say any problems, but most problems that have squareds in them, you want to set it equal to 0. So I'm going to subtract the 16 over to the right. It's going to say 0 equals x squared minus 6x minus 16. And now we can factor, right? So to factor this, I'm going to say what numbers multiplied to negative 16. Those same numbers should add up to negative 6, and we do have values That would be negative 8, okay, and positive 2. Okay? And so when I set each of these equal to 0, when I set x minus 8 equals 0, I get an answer of 8. Okay? And when I set x plus 2 equal to 0, I get an answer of negative 2. Right? And again, I'm going to look at these and say 8's fine, because when I plug in an 8 right here, I'm saying that one of the lengths of the diagonals is 8 minus 6, which is 2. Right? And when I plug in the 8 here, that one's 8. So that's good. Right? So I like the 8, and I'm going to keep that one. Okay? When I check the negative 2, though, all of a sudden this doesn't make sense, because when I plug it in here, I'm saying that the length of one of the diagonals is negative 2 units long, and that doesn't make any sense. So we're going to throw that one out, and we're going to say in this case the only answer is that x could be 8. The only helpful answer for us is that x is 8. Okay? So here's problem number 3. Okay? We're being given a circle. And inside of that circle, they have an equilateral triangle. So I just want to remind you that an equilateral triangle is a triangle where all of the sides are the same. They're all equal, and they've marked that on the diagram. But for us, what's really important is that when all of the sides are the same, we have another word that we use for that, and that is regular. Right? So if we wanted to, we could get rid of the word equilateral and actually put in the word regular. Okay? A regular triangle is an equilateral triangle. They're kind of interchangeable words. Okay, so really they're telling us that we have a regular triangle with a radius of 12, and so they're asking us to find the area of the circle, the area of the triangle, and the area of the shaded region, which is basically just the circle but take away the triangle. So let's start off with the circle. Okay, so I'm going to focus on the circle itself, which means not the triangle. And if you notice, this O to the edge, okay, from the center to the edge, that is the radius of not only the triangle, but also the circle. If I go from the center of the circle to the edge of a circle, that's a radius. So the area of a circle, again, I'm seeing just the keyword, so I'm going to write down the formula, pi r squared. Okay, r is the same, and they told us r in this case is 12, which I'll add to our diagram as well. Okay, so this is really going to be 12 squared pi, which is 144 pi. So we're done. 144 pi. Okay, and our units are square units. So I'll say centimeters squared. Okay. So it said to leave our answers in terms of pi in simplest radical form, which is why we did not multiply by 3.14. I just left pi in the problem. Okay. Problem number 2 is saying, what's the area of the triangle now? All right, so now we're going to kind of disregard the circle and just look at the equilateral triangle. Okay. This is a regular polygon. Okay, so I'm going to write down the formula for a regular polygon, which is 1/2 apothem times perimeter. Right? And so when I'm looking at this shape, I don't know what A is, and I don't know what P is. I actually have to figure out both. Okay, so A is going to be from the center down to the middle of a side, so I got to draw that in. Okay, and P is going to be all 3 sides added up, which means I need to figure out how much any of the sides is worth. So the way that I'm going to do that is to focus on half of a side that happens to be in this triangle as well. If I can figure out half a side, I can double that to get a whole side, and then multiply it by 3 to get a perimeter. So I have this picture here of this triangle, which I'm going to bring out of the shape so we can kind of look at it a little bit bigger. Okay, and so we have this triangle with a right angle, because apothems make right angles. Okay, it's got a radius of 12. I'm sorry, a hypotenuse of 12, and that's all we know right now. Okay, and so we have to figure out, well, how do we get some other piece of information that we can use to calculate the sides? And in this case, the key is to make a central angle. Okay, we can draw any radius line wherever we want. So in this case, I'm going to draw another radius to this other vertex, and what I just created was a central angle. Right? If I go from one radius to another consecutive radius, I create a central angle. Okay. To calculate the measure of a central angle in any regular polygon, you're going to take how many central angles are there and divide that into 360. So in this case, just kind of off to the side, I'm going to say there's 360 degrees. If I were to draw, kind of go all the way around a circle here and back to where I started, I'm going around in a circle, so that's 360. Okay, I'm going to say there are actually 3 central angles in this shape, and if you want to see the third one, okay, I have to draw up here. Right, so if you notice, I have a central angle here, I have another one right here, and I have the third one on the left. Right, so I'm going to take the 360 and divide it by 3. Okay, and that means that each central angle is worth 120, right? So this is worth 120. But if you notice right here, what I did is I took a central angle and I drew an apothem right down the middle of it, which means that each of these little half sections is worth 60. So I'm going to put that right there, right? This little half section in my triangle is worth 60. I know the apothem made a 90-degree angle, which means this over here is 30. And if you notice, what we have now is a 30, 60, 90. So your rules for 30, 60, 90 say, okay, that the hypotenuse, and I'll write the rule for you if you don't remember it, the hypotenuse is equal to 2 times the short leg. Well, the short leg is the one that's across from the 30. So if I take this and I multiply it by 2, I should get the hypotenuse. So it makes sense that this would have to be then half of the hypotenuse, okay? And then my other rule said that the long leg, which is the one across from the 60, that's the one we're missing right now, okay, that is the short leg times root 3. And now I know my short leg is 6, so I can say that this has to be 6 root 3, okay? So so that's kind of solving the 30, 60, 90 special right triangle. Now we got to go back to our picture and say, well, what did we just figure out, okay? And what we just figured out in this case is that this side right here, this one that's going vertical, is actually 6. That is the A. So I'm going to write my formula now. I'm going to plug into my formula now. Okay, A is equal to 6. Okay, and now we got to figure out P. Well, this 6 root 3 I'm going to put right here, right? And so I have 6 root 3 and another 6 root 3 to make the bottom of this equilateral triangle. That's 12 root 3. And I have 3 of those, so if I say 12 root 3 plus 12 root 3 plus 12 root 3, I get 36 root 3. So my perimeter, 36 root 3. Right, so if I multiply this out, half times 6 is 3, 3 times 36 is 108 root 3. Okay, so that one was definitely a lot more work. Right, 108 root 3, again, it's an area calculation, so I'm going to use centimeters squared. Okay, so my triangle is 108 root 3 centimeters squared. Okay, so now the last problem should be easy. The area of the shaded region is just the area of the circle minus the area of the triangle, which I'm just going to write, and they said, if you notice, up top again, in big bold letters, leave your answer in terms of pi and in simplest radical form, which means I'm not actually going to simplify either of these statements, so I can't combine them in any way. So I'm going to just write 144 pi, which is the area of the circle, minus 108 root 3, which is the area of the triangle. And whatever that number comes out to be when you type it in your calculator, that's going to be the area that we keep. Okay, so that one's a pretty challenging problem. It takes some work involved, but something that we can definitely do. Okay, problem number 4. The area of a regular pentagon has an apothem of 5. Find the perimeter and the area. And in this case, they're asking us to round our answer to the nearest tenth. Okay, so no radicals or anything funny in the problem. So my big suggestion, and it's been my big suggestion all year, is anytime the problem does not provide you a picture, you should draw one yourself, right? So in this case, I'm going to draw myself a regular regular pentagon, and they said that the apothem is equal to 5. So from the center to the middle of a side, okay, there's my 5, okay? So I'm going to say this is worth 5, okay? And they want to know the perimeter and the area, which basically means I need to, again, for the area, do 1/2 AP, okay? I know A, they did give that to me, so I really need to find out how long are each of these sides. That'll find me both area and perimeter. So again, I'm going to draw in a radius line, okay, like this, and I'm going to draw in the other one just so we can get the central angle, because we're going to pretty much do the same thing we did in the last problem. Okay, in this case, when I go to my calculator and I type in 360 divided by 5 to get the central angle, I get 72 degrees, okay, and then the 72 degrees gets split up into 2 equal parts here, so that each of these is worth 36, okay? So this is 36, and that would make this one 54. So my triangle now, again, if I pull it out of this shape and so I can kind of focus on what's going on in the triangle, okay, it looks like I have 36 degrees, I have a 5 and a right angle, and what I'd really like to know in this problem, remember going back to the original pentagon, is how long is this? So that's the bottom. So this is a problem that is not 30, 60, 90, it's not 45, 45, 90. We don't have the Pythagorean theorem because I don't know 2 sides. My only other option to solve right triangles is to use trig, which is SOHCAHTOA. So sine, cosine, or tangent. And in this case, we're going to say opposite is x, right? So let me label my sides. This is opposite. And 5 is adjacent. It's also a leg. My blank side here, the radius from the pentagon, is actually a hypotenuse, right? So I'm going to say, in this case, opposite and adjacent means we got to use tangent. So I'm going to set up my equation. The tangent of 36 degrees equals opposite over adjacent would be x over 5. So it looks like when I multiply both sides by 5 times tan 36, that's going to be my x value. So let's go to the calculator again and figure out what that is. Okay, so 5 times, and then I'm going to do tan 36. Okay, that was going to be about 3.6. They said to round to the nearest tenth, so I can leave it as 3.6. So I'm going to say 3.6 is x. And so again, let's go back to our pentagon and see what does that mean. Okay, so I have x is a half of one side, so I need to take my 3.6 and double it. Okay, so I'm going to say times 2. Okay, so that's about 7.2. Okay, and then I'm going to take the 7.2 and I'm going to multiply it by 5 because I have 5 sides. And so it looks like my perimeter is almost exactly 36. So let me just double check that. 3.6 times 2 times 5. Yes, that's about 36. Okay, so I'll say my perimeter is 36. Okay, and now I can actually do the area as well because remember I needed perimeter for area. So let me just move my little, moving the whole thing. Okay, I want to move my formula up a little bit. Okay, and that is not 0.36. That's just a stray mark. Okay, so let me fill in now. I'm going to say area equals 1/2. My apothem still 5. They gave that to us in the problem. My perimeter we just calculated is 36. Okay, so I am going to do 36 times 2.5, which is half of 36, not 0.25, 2.5, and that comes out to be 90. So I'm going to say 90. Okay, rounded to the nearest tenth. I don't even need to round because this comes out working out pretty evenly. Okay, it's about 90 centimeters squared, and this is just in regular old centimeters. Okay, so let's do one more problem in this video, and then we will pause, and I will pick it up in a brand new video. Okay, so problem number 5. It's asking us to find the length of arc CD. Okay, so arc, if you remember arc length, your arc length formula says arc, the measure of the arc, which is the number of degrees out of 360. And then for arc length, it is pi times diameter. Really just find the circumference of the circle. Right? So I'm going to say arc in this case is 120 out of 360. Okay? Times pi. And then my diameter, be careful, is not 9. My diameter goes all the way across, so it's times 18. Okay? So remember, we're trying not to have decimals and fractions with problems like this. So I'm going to reduce, sorry, not decimal. When I'm trying to have fractions, not decimals, we want to keep the fractions, okay? 120 out of 360 is really 1/3, okay, times 18 pi, okay? Well, 1/3 of 18 is just 6, so I'm going to say my answer here is 6 pi. This is a length, right, of a line, so this is going to be in just regular old inches. It's not an area, so it's not square inches, right? So that is the answer. That's a pretty straightforward one. It's just applying the formula. Okay, so I'm going to stop the video, and I'm going to pick it up in a part 2 where we'll start doing some more arc length and area of sectors.